Okay, so we'll go ahead and get started with this. Thank you very much for joining in on today's webinar. We're going to be talking about combining data from different 3D scanners and how that can be used for improving results in 3D scanning. This is primarily going to cover the Artec 3D scanning systems. And if you're unfamiliar with the format of how we do our webinars, we do a Q&A session at the end of our presentation. So if you have any questions at all, there is a Q&A chat button inside of Zoom that you can ask any questions that you'd like, and we will be happy to answer those at the end of the presentation. And today's presentation is going to be covered by Art here in our office, and he's really going to cover a lot of the scanning advantages as well as the processes involved in working with multiple scanners to create really high accuracy and good quality results with these systems. There's an example here that Art will go into some more detail on as far as using really large scanning systems like the Ray all the way down to the Space Spider and even the Micro for creating complex assemblies that have really high levels of detail on large parts through a couple of really interesting processes. And this is something that we can use across a large number of industries. So one of the big reasons why we decided to do this webinar is there's so many advantages, whether you're dealing with manufacturing, medical, cultural preservation, or educational type applications. Being able to combine scan data from multiple systems has a lot of real benefits. So before we get started with the bulk of the presentation, there is one last thing that we're going to do differently on this webinar, which is after the webinar, we have a after hours session where Art and myself will be doing some live work with the scanners. So if you have any more detailed questions or you want to see some things done right there on the spot in person, we'll have about an hour-long session where you can ask us to scan anything that we have around the office or any questions, and we'll be more than happy to do a casual hands-on approach with showing you how to work with some of these tool sets. So with all that being said, I'll go ahead and kick it over to you, Art, and you can go ahead and get started, and I'll jump in closer to the end and try to answer any questions as they come in as well.
Yeah, how's my audio sound?
Sounds good.
Great. So we're putting on this webinar today because we find that our clients are sometimes finding the need to capture extra resolution in objects or higher accuracy for reverse engineering or metrology or other applications. And we know that the Artec line of scanners are a really great solution for that. The scans align really well together and the software is able to process that data well together. So today we wanted to show how we can do that and demonstrate 3 different scenarios. So throughout this presentation, if you've got questions, go ahead and ask, but we'll be discussing the advantages of the large scanning volume of some of the scanners and then the higher resolution and accuracy of others. So we'll demo all of the scanners today, the entire lineup, and that is the Micro, the Space Spider, which are the kind of the front runners of that high resolution scanning, to the EVA, the Leo, and the Ray. So all of that scan data can be aligned to create a lot of volume and really high detail, as well as sometimes you needing to have reference for your scans. So we find occasionally customers need to scan something that's really difficult to register, and so they'll use one scanner for almost a reference purpose, where they'll scan an entire tray of tools and then align the Micro or the Spider scans to like a set that's already there. So let me Go to the next slide. So today I'll be showing a few parts that we've scanned here in the office. And here's a motorcycle frame that we have available on our Sketchfab page that you can look up our Sketchfab account by just searching for Go Measure 3D as a user on that site. And this motorcycle frame we've scanned in with both the EVA and the Spider. And so here are the different scans that I'll show how we can align and process out into a higher resolution model. As well as there's a couple other things we'll show, but here are a few scenarios where people have used combinations of scanners to accomplish a goal. So this was a stone that was scanned with the Space Spider and the EVA, and researchers actually found that they could find certain symbols that were not visible there before from just photographs. And so this led to a certain discovery for these researchers. These models are also available on Sketchfab under Artec's page. This is a really, really large mechanical part that's about 1 meter long. And so it was scanned with the Leo, and then the Space Spider was used for just the end of it to get the threads here, as you can see. And that was used to increase the resolution of this part where it really mattered for reverse engineering purposes. And as you all know, if you've used the Leo, it's a very easy to use scanner. And so capturing this part took no time, and you didn't have to scan the entire thing with the Space Spider, which is really great for high resolution applications, but a little bit of a pain when you're scanning objects that are larger than, a shoebox size. So again, this model is available on Sketchfab. As well as scanning for higher resolution, sometimes having multiple scanners helps you scan challenging objects. So this is a kayak that was scanned with the Leo, and the high detail was added with the Spider. And again, the scanning volume of a scanner like the Leo or the EVA that is much, much larger than the Spider or the Micro allows you to capture an object in really large frames, and that makes tracking much easier. So you've got really smooth parts to this kayak here, and the Space Spider wouldn't be able to track very well as it's taking photographs almost like a macro lens, and going from one spot to another, it wouldn't really see a lot of reference material. So having the Leo here to scan the entire boat, and then to add the detail into all of those little parts there with the Spider made that possible. And another reason we find people are scanning with multiple scanners, and that is to get deeper into certain cavities. So the distance between cameras on these scanners, they all vary, and the Space Spider has the camera is much closer together, and it can see into smaller cavities better than scanners like the EVA and the Leo. And so here's an example of being able to capture more detail. And we all know, if you've used a 3D scanner, that it's an emerging technology, and it's not perfect, and it's got its limitations. So when you want a really large scanning volume, you give up on the ability to scan into like really small parts. And so this again is being able to bring the best of both scanners together. And now I want to show you how we can combine scans in Artec Studio 15. So there are 3 different ways to approach this. We can combine raw scans, and the software, it's very natural for the software to combine raw scan data from all of the scanners except for the ray. The nature of the file format from the laser scanner is just very different, and so there's a separate process for that, and we'll cover that at the end. But the first one is combining raw scan data from multiple scanners. And then the second demo will be combining fusions. So you can complete your processing and your different scans, render out your fusions, and then combine the fusions together. And that has its advantages as well. So we'll cover that in the end. Okay, so you should be able to see my window here. And so this is an example of this motorcycle frame that you saw earlier, and it's been scanned. I'll show you here with the EVA and the Space Spider. So these are the scans from the EVA, and they're pretty good, but there are areas here that are not going to be captured as well as the Space Spider can capture. And we want a little bit more accuracy in the distances between certain tabs here, for example. And so we went ahead and scanned this with the Space Spider. So as you can see, all the parts that were really important to us, we scanned, and we're able to add that detail by aligning these scans together. So alignment happens, as you already know, in the alignment tab, but if you can see the instructions on the right of this window, I've got the workflow written out. And so we'd start by collecting the scan data as we normally would with both scanners. And then we would process out the first scanner. In this case, we'll do the EVA scans as you normally would. So you would process it out in the Tools tab and making sure that you have the presets set correctly. So these are HD frames from the EVA, and you have to make sure that you change it to that setting. There are a lot of parameters you can change in here with registration, but there are other things that you can't that are controlled by the preset. So you have to make sure that the preset is correct. And you'll hear me repeat that many times throughout this presentation because it is very important. And you would run your global registration. For HD scans, we don't need to worry about outlier removal. And then we would stop before running a fusion. And we would do the same for our spider scans. So again, running global registration, if you need to go back and do a rough and fine, but we usually start with the global, and then running an outlier removal for the spider scans, and then stopping right before the fusion. So we've got good clean data here, and it's ready for alignment. So before we do that, we want to lock our most accurate scans. So in this case, it could be the micro or the spider, and the spider scans we can lock to make sure that a registration to the EVA data doesn't move it out of alignment, because this is a scanner that has higher accuracy. So the way that you can do that is you can lock registration in your object panel. So let me show you. There's a lock symbol that appears on the right side. So you want to have that visible. And after you've locked the most accurate data that you have, you can go through with the alignment. So the alignment goes as normal. We would make active our scans that we want to align, and only those scans. We would go to our Align tab. And in here, if you double click, you can register the scans that you don't want to move, and then you can highlight by shift clicking the scans that you want to move, and you can align them together. And so sometimes you can do manual alignment pretty well. Sometimes auto alignment works really well. And you can also always do pair alignment. So in this case, I'm not gonna do anything that'll slow me down. So you would normally hit align and then hit apply. I've already aligned these scans to save us some headaches in case we have any technical difficulties. And here we are with our scans that are aligned. So at this point, we can run global registration. And for this process, we also have to lock our most accurate scans. So I'll unlock these, and because I didn't have the right ones locked, and make sure that registration is locked on the spider scans. And so in here, you have the EVA scans unlocked and the spider scans locked. Now we're ready to go and do our global registration. So we have to switch our preset to the largest scanner because we're looking at this as a whole. And if we processed out the spider scans last, we would have had this preset set to the spider. We just have to make sure that it goes back to the EVA before we do a global registration, since that's going to be affecting the EVA scans and not the spider scans, being that they're locked. And so here you would run your global registration after the alignment, and that would just make sure that everything is really perfect there. And after that, we will go to removing overlapping data before we run a fusion on all of these scans that are combined. Now, there's a lot of conversation about erasing overlapping data. Some people get really good results if they don't. We recommend that you do. You should always leave overlap between the scans so that there is a smooth seam. But in the areas where you want the most detail, we recommend erasing that data. And the way that you would do that is you would go to the editor tab and use our eraser tool. Hopefully nothing crashes here for me. So some of the eraser tools are simple here, but I'll show a tip today that'll help you erase selectively just the areas that you want to erase. As you know, if we have both of the scans enabled and we make a selection, it'll select everything. It'll select both the spider and the EVA scans. What we want to do here is only erase the EVA scans, the areas where the EVA scans may degrade the quality of our higher resolution scans, which are the spider scans. And so, as you know, if you make a selection, you'll select both of them. And if you deactivate that scan, it does not deselect it. So if you hit erase, but you have deselected the spider scans, as I have now, it'll still erase the selected areas in those scans. So there's a trick to doing this. And the trick is deselecting just the spider scans. So here I have an area that I know I would like to reserve for the spider data. So I'll use my just selection tool here, selects all the way through. And now if I deselect the EVA scans, you can see that the spider scans are still selected. And even if I, again, deactivate it, it's still going to be erased if I hit erase. But the trick is just turning off or deactivating the EVA scans and then using your deselect tool. So when you hit Control Alt and brush over it, it's going to deselect only what's active. And now when we make the EVA scans active, we can see that if we hit erase, it'll only erase the EVA scans. So in this case, I've got this part here that is, if I turn off the spider scans, you can see this area has been cut out of the EVA scan and it is still there when we bring back the spider scans. So you would go and do that with all of the areas. You can do this in an entire batch, much larger than just this area. You can leave a little bit of overlap. It's always good to have that, but the areas that really matter, leave that only with the spider data. So after you've done that, you can run a fusion. And so running a fusion requires deciding on what kind of resolution you would use. So we can do a sharp fusion here. And I think I have a slide for this. So running a fusion from EVA and spider data, you'll know that you have to decide what your target resolution is. And it's based on the quality of the scan data that you've captured. So usually for the EVA and the LEO, the target is anywhere from 1 to 0.7. Or if you're using HD data, it can go from 0.5 to 0.2. And with the space spider, we're generally working somewhere in 0.3, 0.2 area. But if you run EVA data at that higher resolution, you know that you'll get certain artifacts, and you may even lose data. You get holes. So you've got to find a combined fusion. And so we recommend starting somewhere in the middle, and then you'll have to iterate and work your way up or down. So if you've got artifacts and orange peeling that is showing up, you may want to move to slightly lower resolution. So maybe in this case, a 0.7, or if it looks good, you can try a sharper one. And so it'll take a little bit of time, and there's not a one size fits all solution for this when it comes to raw data. It'll just depend on the quality of your scan, what you're scanning, and I guess the size of the project as well. So after you've erased your overlapping data, you can just make sure that all of that is missing. In this case, I'm not going to show you the rest of it just to save us time. You can then go back to your tools and then run your fusion. So in this case, actually, I've got really, really good HD data from the EVA, and my error ratings are really good. So I can probably target that resolution. And as you should already know, you can always expand your scans and look at the frames and sort them by their error value and then delete certain frames. So in this case, if just a handful of them are lower and it may not affect the entire scan, you can even push that resolution farther. So after you've done that, you can change that setting here just as you normally would, and then decide whether you want hull filling and then run the fusion. So that'll probably crash my computer right now with Zoom running, and I'll show you what the final result looks like. So this is what we get from combined scans. We get really nice, crisp detail. And if we compare it to the EVA data without the spider scan added to it, we'll see that there are some areas that did not scan as well. So the pink here being the EVA and the blue being the combined. All right, so the next demo will be showing how we can combine fusions. So combining fusions is useful when you can get most of a part, one end of a part scanned, and it's really good and there are no holes in it. And you can push the resolution a little bit further here because you can use separate settings for processing the two scanners' data. So let me just close my other window. So clear a little bit of memory here. And so this is a scan of a drill here, and we did this with the spider and the micro. So here's the raw data from the spider, and it was done in 2 parts, aligned. And again, as you can see, the workflow shows you would just capture your scan in a regular way. In this case, we had it on one side, flipped it over, scanned it, aligned the 2 scans, but we wanted more detail here in this in this area right here. And so we took that part out and actually scanned it with the micro. And so this is the micro scan where we did it in 2 parts again, the back end and the front. This is a really simple example. You can, of course, do much more complex parts. And you see that was done in almost 60 frames there. And now we can process this out into separate STLs because we can really, really push the resolution of the micro fusion much sharper than what we can do with the micro. So we might not want to split the difference here. And so you would do that in a normal way, but remember, you've always got to check your preset. So we've got the micro data selected, it's activated, nothing else is selected. We go to our tools. I've already done the alignment on the 2 parts of the scan, and we would run a global registration and then do a sharp fusion. So for this data, it can be to almost a 10 micron level, and that's something that you can set here, change it to be watertight, and then run it. And so what I get in the end is these 2 fusions that you can see there's more detail that I want out of this micro scan. And so this is a dirty part, so there's some dirt that was scanned as well. But to align fusions, we would change our preset back to the bigger scanner because it's looking at it as a whole. So we've got it set to the spider, and that's good. And then we would just do our normal alignment in here. And again, you can use pairs. So you can click on parts of one scan and then the other one. You have to make sure you have at least 3 points and that they are not on the same plane. So then they're not flat to each other. So once you've aligned those markers, hit align, and then it'll do its registration. And I won't do that now. I've already done that. So here are the aligned parts. So these are fusions. Again, we're working with fusions here, and we've got different resolutions that we would like to combine in these scans. So in this case, I would make sure that I am erasing the part that I don't want. And something like this, you don't even have to show the micro data. I could probably just slice off the top. But just to show you what the tip is, you've got to select. It helps to have both of the scans visible because you know exactly if you're erasing too much. So you want to leave enough overlap so you can have both of them visible. And so when you just select the area that you would like to erase, again, you can, let's hide the spider data and then deselect this. And so now we can just erase data from the spider scan. So once that is erased, you have enough overlap there that it's going to fuse together really well. And here you would apply the same principle. You would not set the resolution too high. but find something that is acceptable for the spider, and you'll see that you'll still have a lot of detail that's left in this after you run that fusion. So you can change it to be watertight or not, and make sure that the preset again is set for the larger scanner, and I think something like a 0.2 would do really well here, and you can run that fusion. So this is the final result, and let's take a look at what it looks like compared to the original spider only scan. So as you can see, we still get a lot of the detail that's left over, but where it matters, we've got that higher resolution. And so that's how you would combine fusions, and certain applications, that is something that you may choose to do. All right, so the last demo is combining array data with raw scan data from any other scanners. You can, it's probably unlikely that you'll do a micro with array, sometimes maybe a spider, but usually we see EVA and LEO data being aligned with a really large array scan. So outside of our office, we've got a train sitting here, and let me just close this window here. So we've got a train that sits outside, a train car that sits outside of our office. And so did an experiment of scanning an entire building behind it and then the train car. I only did one scan just to make this a lighter file, but of course, something like this would normally be scanned from a few positions, so we get the measurements of this train car if that's what we needed. We can scan it from the back end. And then I focused on this area here, this hitch that I wanted to get more detail in. And so I pulled in the Leo, being that this is a really great wireless scanner, much like the Ray, which is also performs well outdoors. And we're gonna show you how you can align that. So here, the thing about Ray data is that it's gotta be triangulated or fused first. So a triangulation is a quicker way to get a mesh out of the Ray. And then the fusion is there's more control that you can have over the resolution of it. And you will find that playing with both of them will get you different results. So in this case, I have triangulation that looks a little bit better than a fusion does, but both of them are meshes and they will align well with our Leo scan. So the Leo scan, this is just the raw data here. I've run the global registration on it, and it resulted in this 0.4 accuracy. So the way we'd want to do this is very similar. We would make sure that our presets are set according to the data that we're processing, and then we would lock our handheld scans and then align that to our array data, except for situations where the ray is closer to the object you're scanning, 15 meters or less, you'll actually get higher resolution from the ray that you'll get from the Leo. And so in that case, the data from the ray is supposed to be more accurate, and we would take the Ray data and lock that and register the Leo data to it. Whereas if the scanner, as in the case of this train car, is farther than 20 meters, we assume that the handheld scanner is more accurate. And in this case, also, I was able to walk all the way around it. And so we don't have a lot of data from the ray. We're going to lock that. We're going to assume that the LEO data is more accurate. We're going to lock it and align everything else to it. So just briefly, this alignment works the same way. You could move it in and hit align if it's close enough, and that'll get you a quick alignment. So after that, we would run global registration, but as you see, I've locked my LEO scan, and the ray is unlocked, and in our tools we can just run a global registration, but the preset in this case is going to be for the LEO. So after that, we can remove overlapping data, and similar to what you saw me demonstrate before, you can just go in there and erase it and then run a final fusion. So this is what it looks like in the end. Where you've got this part that is scanned from every direction, and it's something that would not have been captured with the ray. So here you can also play with the resolutions. This is something I did quickly, and I think I can get better resolution out of this if I combine. Also, in this case, you can combine your fusions. So if you want to just completely cut away the ray data, you can do that and get a much higher resolution on the LEO, as we showed in the second scenario. But this is how you would align ray data with LEO data. So that's most of the presentations. And now, Paul, we can get back and talking about the pros and cons of the different ways of doing this.
Sure.
So
Yeah.
let me know if I've missed anything.
No, I think you've done a really good job with all this. So thank you for that, Art. And with these three different processes, there's actually some questions that have come up that I think will be really good for blending into the pros and cons. So first and foremost, pros with this, as we've already discussed, when you're dealing with data from multiple sensors, it gives you a lot more flexibility in the parts that you can scan and the details that you can pull out of those parts. I think that train example is a really good one of showing we can take this really large area and get all of this data for measurements purposes, and then really refine in small details and use those measurements in those smaller areas for whether it's reverse engineering or inspection processes. You get the best of both worlds. I'd say, when we're really talking about cons, there's two major aspects to this. One is time. So, you can capture scan data with one scanner relatively quickly, scan it, pull that file together, and then you have your mesh without a lot of other processes being put into place. Whereas when you're using multiple scanners, there are some specific steps and some knowledge that you need to have to be able to pull that off in a repeatable manner, which is really what we've been discussing today. And there's a couple of things that have come up for questions in that pro and con list I'd like to talk about. One of which is when you're scanning two different objects. So generally speaking, you're going to have a large scan and then you're going to have a small scan. So that large scan could be a ray file, it could be an EVA file, it could be a LEO file. And generally speaking, that smaller scan is going to be either a spider file or something coming off the micro, or it even could be an EVA scan or a Leo scan when compared to the ray. So in the when you're dealing with these scan files, which one do you prioritize? And Art, you covered it really well for the Leo versus the Ray, as there are specific distances in which the Leo is going to have a higher accuracy versus the Ray, and then there's other distances at which the Ray will actually be a little bit more accurate than the Leo, so we can prioritize one versus the other. When you're looking at the rest of the scanners, though, I think like the motorcycle frame is a really good example of this, where uh, we would probably prioritize the data coming off of the larger scan first uh, rather than the smaller scan because we have more detail. So, or we have more, not necessarily detail, but a larger overview of the part. For instance, in that frame, we would want to align all of that EVA information first, get that locked in place, and then patch in the network of spider files because they're not going to be cohesive to one another. So if we tried to deal with just this small band versus the entire piece, we're better suited to get the entire object locked in place first and then come down into the smaller segments. Uh, but it is a little dependent upon what you're scanning and how you're going to go about generating that whole file. But I think a good general rule of thumb for which scans you prioritize, especially when we're talking about it just from a raw data standpoint, is going to be which one has more information for accurate alignment. So, in previous webinars, we've talked about how to make sure that we're creating really accurate scan data and how we're going through our alignment processes and the things that we keep in the back of our mind. You still want to apply that when you're looking at a spider scan compared to an EVA or a Leo versus the micro. So another question that came up is minimum overlap.
And just to add a little bit to what you're saying, there's accuracy on a scan kind of level and then on a volume level. So when you scan just like the tabs on the part of that motorcycle frame, you're going to get, it is more accurate out of the spider, but that scan in relation to the other scan of the other tabs across the frame, that distance there, the farther away you get, the more you lose some of that accuracy. So as Paul, you're saying, in that case, you would want to prioritize the entire EVA scan for the positioning of those other scans. But within the scans specifically, it is still more accurate, like a spider is more accurate. So you have to think about what kind of issues might come up. And like you're saying, Paul, there was like 5 scans across the frame with the spider, and just to make sure that those scans are in proper positioning, we would prioritize the EVA.
Exactly. Exactly. So let's go through a couple more of these. When we're talking about removing data for the overlap process, so if you have scan information that's overlapped, there is a minimum amount of overlap that you want to retain. So you can keep as much overlap as you want. As you saw in the example that Art brought up, on that frame, there's a really big section of overlap between the EVA and the spider. But as far as minimums go, you're going to want to keep a minimum of at least 10% of the coverage of one of the scanners. So your smaller scanner, so like 10% of the data that you've got, you want to have that overlapped in a band in order to make sure that we're getting accurate fusion process to occur. So let's see if I can kind of, like on that motorcycle part example, if there's a tab and then there's an overall frame, we want to have at least a 10% of whatever that particular object was overlapped. Kind of like if this is that little tab area, we're going to want 10% of whatever this is to lock into place. And that is a little open to interpretation. So for instance, if it's a really long part, you don't necessarily need to keep 10% of the overall volume of that object in mind. you can start looking at it from actual sizing. So having maybe a 2 centimeter overlap would be more than adequate in pretty much any scenario. But outside of really specific applications, if you could just look at one particular file and make sure that you've got 10% of that that's covering the other one, you should be good to go every single time.
And that's for alignment. We always say that for alignment, when you're scanning with different scanners, you just want to have your scans with this at least a 10% overlap. If when it comes to, I don't know if you're going to talk a little bit about, Paul, the actual like erasing data, that overlap, it doesn't have to be 10%. It's whatever you want it to be. The transition area, basically, if you can get it close, you still want it to overlap. There'll be less of a transition area. You won't have to smooth it out. And that just gets back to also another point I was thinking about with the pros and cons. That first scenario, combining raw scans, I think we had a question, somebody was asking, as a general rule, is it better to combine fusions or the raw scan data? Well, again, always depends, but in the case of the motorcycle frame, the raw scan data very naturally fits together, and so it's better there. And you're not going to get a transition that like a seam that you would if you're combining a fusion, because with fusions, they are very, very precise surfaces that have been already rendered out and kind of locked in place. And so you'll have to go in and smooth it out. Whereas if it's still the raw scan data, there's a whole lot more information there that the frames can mesh together and have a smoother transition. And so then there's no further editing required if you were to combine fusions. So
Right. Yeah, and I don't know what your thoughts are on this, Art, but from a general rule of thumb, if you can work with the raw data, it's better to go after that from an alignment standpoint. Because if we're going to if you're going to take all of this stack up of information and run a global registration on it, the more, and I know this gets a little tricky, and this is kind of going outside of the processes that you've really discussed here, but in certain applications, if you can run a total global registration between various objects, like if there's a real mission critical part in a dimension, this isn't maybe necessary practice or standard practice, but at that raw level, you have a lot more control over exactly how those fusions, or at the raw scan files rather, are going to start to interlace into one another.
mhm.
There are pros and cons to that, and that's more something that if somebody has specific questions, we can do some examples of playing around with how that can be good, but also how that can kind of get sideways on you really quick. But generally, I would say, looking at it from a raw standpoint, it's going to give you a little bit more flexibility on accuracy, but also even in the from a fusion standpoint, you do have a lot of flexibility. Even if we look at like non-rigid alignments and how we can kind of manipulate parts into place, there's a lot of different processes that can still give you a lot of accuracy. One of the things that I try to keep in mind is I'm going to go through and scan with multiple systems, map out how you need to scan that part first, like visually in your head. If you could figure out, okay, this dimension from this point to this point, I want the accuracy of the spider, whereas these other dimensions, I can take the accuracy of the EVA, and that can help you to really start to figure out exactly how to, which process to use and how to go about tackling that scan. So hopefully that all makes sense.
Sure.
Do you want to add anything else to that, Art?
I'm just thinking a few more like pros and cons. One of the cons to combining raw data is that you can't always push the resolution as far as you could with individually processing out the fusions. So sometimes you can just really push. It's minor differences, but again, it depends on your parts, and if they're aligned really well, you may choose to do a combination of fusions because you can, like in the case of the micro scanner, it's just much more accurate there, and most of that tooltip was aligned really well, and so we just completely discarded the spider scan, and then in that case, it worked really well to get this like really high resolution. And so if we were to do a combination of the raw scan data there, I think that the gap in resolution between those scanners would have kind of brought down some of the quality of the micro scan. So,
Sure.
but this is why we present kind of these different scenarios so that you can experiment in different ways and figure out what results you get,
Yep,
best results that you can get for your application.
exactly. And then there's one other thing that I wanted to kind of bring into this, which when you're dealing with scans from multiple systems, multiple sensors, there is one trick that we can use to make sure that everything's kind of locked into place, like a little bit of a sanity check. Which, Art, do you still have that Ray file to where you could open it up real quick?
Mhm.
If you could zoom in on the uncombined one where you have the Leo data and the Ray data aligned, uh, there's a there's a really interesting thing that we can do. Actually, go to the one that's got the global registration combination. So actually, before you do that, go back to the other one and I'll explain this kind of in some detail. So if we look at this first example of our Ray data and our Fusion data, or our Ray data and our Leo data rather, there's orange, which is representing the Leo, and then green, which is representing the Ray. And we can see both of these files are close to each other. But how do we know that the Leo data is actually accurately registered, and also that all of the information that was processed between the two are going to be accurate, within the specifications of the systems in their relative coordinates in 3D space? Well, we can visually look at this one and say that there's some work that needs to be done because we don't see any interlacing of the two scan files. And what I mean by that is if you can just hide those two off, Art, and then show the global registration. So after global registration, now we can see anywhere that the Leo data interlaces with the Ray data, we have this sort of salt and pepper type of looking texture where we can see those two scan files literally sitting right on top of each other. So visually, whenever you see this sort of interlace between two scan files, that is a really good cue to know that first off, they're accurately registered to one another, and also the overall dimensional accuracy between the two systems themselves are correlating to one another. So if you look at that from an XYZ dimension, we can see in X they're almost identical, in Y they're almost identical, and in Z they're almost identical. Really what we're doing with the Leo is we're bumping up the resolution now. So we have that same general information aligned in a much more, or we have high resolution that's aligned with the same accuracy, if not greater, and in a way that we can do whatever processes that we want to with that higher resolution information. So those are the basic things as far as the pros and cons, as well as, we went through the majority of any of the unanswered Q&A questions through all that. So what we're actually going to do now, well, first off, Art, is there anything else that you'd like to add to this?
I
I
think
think,
we can address that in the next meeting.
yeah, no, that sounds good. So you've given a lot of really good information. So what we're going to do is we're actually going to go ahead and jump off of this webinar presentation, and we're going to go over to just a regular Zoom meeting. So with the webinar presentations, you can see us, we can't see you. You can ask questions, but we can't all really interact. This next session is going to be just like a standard uh, Zoom meeting that you have probably been on millions of over the past year. And Art and myself are going to have some scanners. We've got plenty of different parts, and we're just going to play around with some of these processes, scan some parts, and really show you whatever you'd like to see for about an hour. So one final question, there's when will we have access to this recording? So once we finish this recording, we'll process it and there will be an email sent out that will have this recording available to you. And as soon as we get that all finished up, we'll go ahead and send a notification to you where you can view this at any point in time. It should be within the next day or so that you'll see that information.
All right, so I'll
Yeah.
leave this last slide up. If you want to have a suggestion for us for another webinar, you can email us at info@gomeasure3d.com. And
Yep. And then one final thing, I did put the link for the webinar we're about ready to, or the Zoom meeting that we're going to do here in just a moment, into the chat. You also should have an email that has this link as well. So either way, however you want to join into that, you can. And let's see, is that everything that we were going to cover here, Art?
Yes.
Cool. All right. Well, I'll go ahead and get the Zoom meeting started, and we'll see you all over there. Thank you very much for watching this presentation, and we'll talk to you soon.